So Unmesh works at ThoughtWorks and is going to talk about patterns of implementing consensus. He's hopefully going to also show us some code that he has written, be able to simulate some of these algorithms and walk us through that. Should be an interesting talk. Over to Unmesh.
Thank you. Okay, so good morning, guys. I'm going to talk about patterns of implementing consensus. And the title is pretty heavy, but the talk won't be, I assume. Because one of the motivation for doing this work that I'm doing is there is a lot of confusing terms that you read. So if you search for consensus, there are a hell lot of terms that you hear, like raft, Paxos, FLP impossibility, and networks and time and all of that stuff. If you go to any of the books, they are all very theoretical. So you go to any distributed systems book, they have a very theoretical information about how Paxos or even raft is implemented. Raft thesis, by the way, it's one of the most practical descriptions, but still it's hard to read and understand what's going on. So the approach that I took a few months back was to stop reading books and start reading code bases. So I started reading Raft code. Raft has a reference implementation called Lock Cabin. There's a very good Raft implementation in its CD. Zookeeper, along with some of the other distributed systems like Kafka and Cassandra of the world. And then I figured out that there are a lot of common things that you see in all these code bases. And if we capture these common things or understand how they look in, say, Java code or Golang code, it's very easy then to understand if you go back and read a book of what that book is talking about. So I've tried to capture some of these common things and approached it in a way of patterns, because patterns, I think, why I chose pattern format is instead of just giving descriptions or the solutions, which most books do, pattern format talks about problem first and then the solution to that. And that's the reason I chose pattern format. So let's look at some of the problems that most these systems that implement consensus, most distributed systems, they try to solve. So first is how to recover server state from a cache. So you're making state changes, like assume a KV store, a simple hash map. You are putting key values in a hash map, and your process crashes. You need to recover your state in a stable form, and that's what is the first thing, durability guarantee. The second is now you need to be available and consistent even when your server crashes. So you need obviously multiple servers. Then the next question comes, how to decide how many servers I need. Do I need 1, 2, 3, 10? How many of them are enough? And the next question comes is, if I'm now updating state on multiple servers, when to say that my state is successfully updated, right? When do I tell it to the client that you are, again taking a simple hash map example, let's say you are putting a key value. When do you tell client that your key value put is successful? And which server does the client connect to? If you have 3 servers, which one the requests go to? Do they go to all or one? That's the decision that you need to take. And sixth, I'm ahead of myself, but I'm talking about leaders and followers, which solves some of the problems that we talked about. But how do these servers communicate with each other? Do they maintain a single TCP connection? Do they maintain a connection pool? Do they open a connection on demand? How do they do that? And the next one comes is how the requests are processed. I mean, what coding blocks typically are used to process requests within a server. And then the next ones are just knowing if your servers are alive. What mechanism is typically used. And also to know if there is a network partition and the server was disconnected from rest of the cluster, how to detect that. So these are some of the common problems that you see solved in all the implementations of distributed systems, particularly consensus. That's what we are focusing on. So in the pattern format, patterns, as you know, are like recurring solutions to problems in a context. Solutions to these 9 problems essentially look like this, and we'll go through all of these one by one, also seeing code of what these things look like. So the primary implementation pattern is write-ahead log, and again, the problem there is in case of server failure, after your server restarts, you should be able to preserve or again get the state back in your server, right? And the solution is pretty simple. It's like implemented in every database. All consensus implementations typically do that, is to maintain a single file, single append-only file, and every mutation, every update that's happening or that's getting processed is first appended to this file before it is applying. And only then you return a success. And examples, as I'm saying, is every database. And on restart, the first thing that you do is if you have a write-ahead log, you replay that log to get your state back. And this is the fundamental pattern. Everything is around this write-ahead log pattern that you see. Now, just to see how it looks in code, so let's say you have a simple key value store, which is nothing but just a hash map. And the first thing that you do when you implement the put operation is you write an entry with the type of transaction. So this is a set value command that is called when you put. It is serialized and written to a file. And this vol is nothing but just a simple random access file, which is appended to. And when you put, essentially, so this is just a simple test saying when you put, you should have a write-ahead log with entry of 1. And when you initialize, when you restart, essentially, just a simulation of a restart, that you should apply your write-ahead log and get the whole state back. Yeah, so these tests run, but you can, this is available on GitHub, and you can go and take a look and even play with the code. But any write-ahead log implementation, like whether it's etcd, whether it's console, whether it's a database, like even Cassandra kind of database which maintains write-ahead log, the core implementation is like this, essentially. Very simple. We've not implemented any snapshotting or segmentation and stuff like that here. But the core code looks exactly like this. By the way, even Kafka, for that matter. So now the next, yeah, this is just a diagrammatic thing that this crashes. what you do is you should be able to read the state. Now the next thing is this gives you durability when your server restarts, that your state is preserved. But how to maintain availability? Like even if my one server crashes, I need to be available. I should be able to serve client requests. And this write-ahead log mechanism, now, I need it on multiple servers. It essentially, to make sure that if one crashes, I should be able to go to second and work. Now, specifically the write-ahead log implementation, which we saw, which essentially just had this write entry kind of a method, write entry and read all. When it goes on multiple servers, it needs two more capabilities. One is to be able to tell if this write-ahead log is up to date with some other write-ahead log, because you always need to compare when there are multiple servers, and we'll see when they are compared. And also should be able to truncate its log if it has any extra entries which are not replicated. So if you see this kind of an arrangement, or a very typical 3-server arrangement in let's say Zookeeper or etcd, and client is setting like 4 keys. In the first server log, the 4th key is appended, but before it could be appended to any of the other servers, let's say this crashes, and the other 2 now, the client starts working with the rest of the 2. Now when that comes back again, it needs to do 2 things. Check if my log is up to date, and if there is any conflict, I need to truncate. So that truncate operation, if you see, that KV4 that was appended to its log, it's truncated after it comes back up. And so this is a extra capability that your write-ahead log implementation needs. And this is again, as I said, examples in every consensus implementation or a distributed log implementation. So some of these are not limited to just consensus implementations. You will see these code patterns in Kafka and Apache Bookkeeper and stuff like that as well. Even in databases like Cassandra, some of these. So the truncate implementation So it's again, if you look at the implementation, like any file API, whether you are using in any language, it allows you to truncate at a particular position. So what you need to always capture is essentially the indexes and the positions, and then you can truncate at a particular log index. But this is how the code looks when you say truncate, and this kind of code you will again, as I said, see in Raft, even Kafka, and does the same thing. Now the third question is then how many servers do I need? Because even if you use multiple servers, you have to make sure that the system as a whole should not be in a conflicting situation, even in the case of network partitions and stuff. And that's where the concept of quorum comes in, that any operation that you do on the server or server itself also should be functional only if it detects that it's part of the majority. And that's what is called as quorum implementation. So what does majority look like? So if you have one server, obviously majority is 1, but then you cannot tolerate any failure because your one server is down, you are down. When you have 2 servers, the majority is 2, but you again cannot tolerate any failures because if one server is down, you do not have majority, so it won't function. For number of servers 3, majority is 2, and you can tolerate one failure. Now, interestingly, if you increase the server by 1, that's 4, your majority is 3, and then also you can tolerate only one failure. So you cannot tolerate 2 failures, even if your number of servers is 4. And that's one of the reasons why you typically see like use your Zookeeper installations or etcd installations, you will have either 3 or 5. You will never have 4 or 6. Because that additional server doesn't give you any additional benefit. You won't be able to tolerate additional failures, but it adds extra latency because you are writing to one more server. So again, the same example, if we look at, and I've shown leader and followers that we'll talk about in some time. But if you see the values which are set in our hash map, even if there are 3 and 4 which are written to the log, they are not applied. Because the quorum of servers yet do not have those values in their log. Now, how do you decide? Now, when I said that the values are not available in my key value store because they are not, the quorum has not replied, right? Because my server I am just appending to my log. So these servers keep something called as high watermark or commit index. And your write-ahead log entries till this commit index are always applied. So if you are putting values in your key value store and your commit index is, let's say in this case my commit index or high watermark was 2, because let's say 2 replicas replied to me that they have successfully added the entry in their log, write-ahead log, I apply that to the hash map. And this is a very, again, because it's a pattern, you see that even in things like Kafka or Apache Bookkeeper. When you say, I need acknowledgement equal to all, in case of Kafka, there is a write-ahead log. So even if your messages are appended to the leader log, your consumers won't see them till the high watermark reaches the end of the log. Now the next question, we had n number of servers, 3 or 5 mostly. Now which server do client connect to? Can it connect to any of the servers and then each one coordinates for every put that happens? So typically not, because you need to coordinate data copying across replicas. And if replicas are lagging behind, someone needs to make sure that they are brought up to date. And that's the reason all the implementations, they typically implement something called as leader followers. So they elect a leader at the start, and all the client requests go through a leader. So it typically starts like this, that you request vote, and after you get a vote, whoever gets majority will be elected as a leader, and then it will process all the requests. So we'll see this in code. So if you see this kind of a while loop, most of these implementations which rely on leader election, they will have this kind of a while loop, infinite while loop, and which has a switch case, and the server will behave depending on the current state it is in. And it always starts in a looking state. So if there are slight variations in the implementations of, in which state the server starts in. Like Raft, it always starts in a follower state. In Zap case, it will start in a looking state. And the first thing it does is it looks for leader. I mean, it just connects with all the servers, all the peers, and sends a request vote. And everyone replies with the current vote. So if you see, the current vote is always, now this implementation that I have done is similar to the Zab implementation, that each server has this single variable that it keeps, like the current vote, which is the atomic reference. And it always first sets a vote to itself. And then it updates this vote based on the responses it gets from the other servers. And the algorithm, if you see, is pretty simple. I mean, if you see, this is the crux of the algorithm, how it votes for which server it selects as a leader. So this ZX ID, if you see, that's a log index ID, which it selects the log which is the maximum. But let's say you don't have any log at startup. So at startup, it will select. So each server has an ID, and ID is numeric. Like ID will be like 1, 2, 3. So it will select a server which has the maximum ID. So if you have 3 servers, and we'll see the test for this. So if you see, I'm starting 3 servers with ID 1, 2, and 3. And I don't have any log because they're starting fresh. So peer 3 will be elected as a leader. So we'll just run this test just to prove that this works. Yeah, so I don't know if you can see the log back because it's too small a font, but I'll encourage you to try this thing. Now this is another interesting things, and if you see all these code bases, right, like the Zab or even Kafka, the tests are written like this. So you don't really need to start servers using Docker containers or different processes. Essentially, each server is an object which you can start on a different TCP/IP port, maybe selecting a port randomly. and then you can assert on their state. So if you see what's happening here, is these three objects, which are three servers. They're started and they operate concurrently, and then tests just wait till a specific state is, you assert on a specific state. So here what we are asserting on is peer 3 should be leader. And this wait until true, it will either time out or it will fail. So it has a timeout internally. So this is an interesting way to test while you are learning distributed systems. Not just while you are learning, you see actual code bases also doing exactly the same thing. But this helped me personally while I was going through the code bases. So this is how the leader election typically happens. Like at the start, you have that infinite while loop, which just checks which state you are in, and the server behaves accordingly. Now, how do these servers communicate with each other? Yeah.
So suppose we have 5 nodes.
Yeah.
And we got 3 grant votes from to one node, and the one node that is giving grant vote has gone down after saying that I am granting you the vote.
Yeah.
And now quorum is not met. So in this case, re-election has to happen, right?
So if your follower goes down, so let's say you have 5 nodes, you said,
Right.
and one goes down, then you are fine.
So yeah, so 3.
Yeah. So if you have 3 nodes
Right.
and one goes down,
Right.
you still have a quorum. You have 2 nodes.
Right.
And unless your leader goes down, so if it's a follower that is going down, it's still fine. Your leader will work. If your leader goes down, then re-election needs to happen. Yes.
Yeah, so so now the leader is not there, and we
Okay.
are trying to elect a leader, and for that we request grant votes from all the nodes
Yes.
to each other.
Yes.
And now in this process, a node says that I'm granting you vote
Yeah.
to become the leader
Yeah.
because I'm not, I don't want to become, and then that node itself goes down.
Yes.
So then the quorum earlier it was said that to one
Yeah,
particular.
yeah, yeah. So so once the quorum is not there, system won't function.
Okay,
Yeah.
thank you.
Right. So next is how do these leaders communicate with followers, or followers communicate with leaders, right? And because we are essentially replicating this write-ahead log, right, across servers, one of the key requirements is that if you see the write-ahead log, the way it is implemented, it's append-only log. There is a strict order in which entries are appended to the log. And that order needs to be maintained even when you copy it across the servers. So one of the simplest things that's done in these implementations is there is a single socket channel which is maintained between leader and followers. So there is a single socket connection, and all the append entry kind of requests, like which copy these log entries across the servers, they go on a single TCP connection, and which make sure that they are always ordered on a TCP channel. So if you see like this message 1, message 2, they are sent on a TCP network in this order. Every peer will receive it in that order, and the responses that are sent also will go in the same order. Now this is the network piece, that the network you are using a single connection. But how the servers process it, like once they receive it on the connection, And this is also true about the client requests, because leaders and followers, they can maintain a single connection. But the clients, when they connect to your leader, they will be concurrent, and there can be hundreds of clients coming to you, opening 100 concurrent connections. But the state update, like the write log entry append that needs to happen in strict order, right? One at a time. So what all these implementations do is they maintain a work queue. And work queue, you can imagine a channel in Golang, or things like array blocking queue or a linked blocking queue in Java concurrent library. And all the connections, all the requests that are coming to your server, they are appended to this array blocking queue or a channel. And then you have a single thread or a single Go routine, which is picking up requests from that channel and updating the state, updating the write log. So again, as I said, examples you will see in Golang implementations, like CD is a Golang implementation, you will see the usage of Go routines and channels, like a single channel operated by a Go routine. In Java implementations, you will see things like linked blocking queue operated by a thread. So essentially, the picture looks like this, that you have multiple requests coming in, but you have a single work queue and a single thread operating on that work queue to process all the requests. And I think I have some code here as well. Yeah, so essentially you see this kind of socket IO. What it does is just submits the request to the queue, and the work queue is this singular update queue I have here. Like I'm using array blocking queue here, but the submit just adds to this queue, and this thread then just picks up values one by one and processes them. And you will see this pattern very heavily used in most of the consensus implementations. But even in case of Kafka, and Kafka is slightly different, by the way. Kafka doesn't use, and we can take it offline, but that's an interesting question I had personally when I was going through Kafka code. Because in partition, single partition, you need to maintain order, right, when concurrent requests are coming to you. And Kafka uses locks, but most of these implementations, they don't use lock. Kafka has a different reason, because Java doesn't have lightweight threads. But that's an interesting point. Most implementations are like this single thread or single lightweight thread working off the queue. I think I should be able to show this in action as well. So, I mean, just to show you what we discussed about Quorum and stuff, how that looks in your key value store implementation, if you want to see. Now, the first thing that happens, as I said, if I start like 3 servers, which are my key value maps, and I put in my leader, right? The put request goes to leader. The first thing it does is proposes this value. So you propose the set value command. That's what is the first request. It appends to its own log, and then it just sends it to all the peers. Now, this, just to simplify, this is a synchronous code that I have written, not asynchronous. Real code will be asynchronous. And then it updates the match index. I mean, match index is just to mark how up-to-date the followers are. And then it figures out what is the quorum match index and applies its commit index. And when the commit index is applied or updated, that's when it applies the values in your hash map. So the put returns only after this whole cycle of message passing is complete. And again, you can run this test. The interesting thing here is if you see the leader election algorithm that I have is the zookeeper one. The replication requests and the commit index implementation is from the raft kind of thing. So one of the benefits of having these kind of miniature code bases and these kind of patterns implemented in simple code is that you can mix and match and see what is the effect of changing parts of the algorithm. Yeah, so the test passes, I think, yeah. Now, one of the other things which is important is how the followers know or how the cluster knows that, yeah, okay, sorry. Yeah.
Hi. Regarding the singular update queue that we have,
Yeah.
so because of having a single worker queue, it would be one thread which will be executing.
Yes.
It should affect the throughput of the system.
Yeah, it generally doesn't.
So how do they kind of...
Because there is no alternative. I mean, if you have to, I mean, one of the things is the operations you are doing are only appending to a log, which is a very fast operation. And you don't have any alternative. So alternative is to use logs. But what you are asking is right. It does affect throughput. You are doing one at a time operations. So typically what these implementations do is they do batching. So instead of like doing these propose operations for single requests, they batch a bunch of requests and then they send it together. But then they are appended to the wall one at a time.
So that would eventually means the latency of the individual request should also kind of...
Yes.
According to the batch size that they have.
Yes.
Okay. Thank you.
Right. So one of the next questions that we need to solve is how do... Oh, you have a question?
Hello. Yeah, sorry, it was once again regarding the singular update queue.
Yeah.
So I was wondering what about the durability of the queue? So if you are submitting requests to the queue and what if the process running the queue goes down? So
no, process running in the sense your leader goes down. If the leader goes down, the leader election will still happen. So the durability of queue is, I mean, that's like a transient state, right? That's the connection state, essentially.
Okay.
Right?
Yeah.
So if that goes down, your connection will drop with the client.
But I was wondering from the point of view of like if my leader is elected and if the leader has like 5 tasks in the queue,
yeah,
and then it goes down, but
no, but 5 tasks. Okay, so this is not the thing is that this is not for asynchronous operations. So this work queue is internal to your server. So your client is still connected, and client connection won't be dropped. I mean, client connection or client won't get a response till that whole work item that is submitted to the queue is processed. So this going down, oops, sorry. So this going down, that means your client connection is dropping, and then the leader election will again happen, and client will connect to the new leader with a retry mechanism that it has.
Okay.
Yeah.
Got it. Thanks.
So this queue is not visible to the outside world. This is how internally the processing happens.
Thanks.
Yeah, so talking of heartbeats, and this is again a very simple concept that every leader, once it's elected, it sends periodic messages to your followers, and that's how followers know that leader is still alive. And even if there is no request coming from leader, they will get this ping request. So every consensus algorithm has this kind of a heartbeat implementation, a very, very simple timer kind of thing. Again, as I said, not limited to consensus. Even systems which implement things like gossip protocol, like Cassandra, they have concept of heartbeat. The implementation is slightly different, but the concept is pretty common, that you send periodically some messages to the rest of the cluster for that cluster to know that you are still alive. And if there is a crash, or it cannot send the request, the crash can be hard or a soft, and we'll talk of soft crash in the next pattern. But for some reason, if there is no heartbeat received from the server, the re-election will be triggered by the followers. Or like if you take Cassandra, like going just slightly outside the topic of consensus, I mean, things like hinted handoff will be triggered, that things when the node is marked as down, because the heartbeat is not updated. Now we talked of this crash, but sometimes this crash might not be a real crash. It can just be a network partition, and when I say the network, some glitch happened because of which the heartbeats did not reach your followers. Or very simplistically, it can be a GC pause. And this is a very real scenario in JVMs. Let's say you were sending or supposed to send heartbeat every 1 second, but you get a GC pause which is 5 seconds. And the GC pause happened right at a point where server was about to send the heartbeat. Then it's an interesting situation that happens, that I will go to this. So your server was about to send heartbeat, and at the time GC pause happens, and when the GC pause is over, it sends the heartbeat to the followers, right? Now, it's an interesting situation because followers did not receive heartbeat for, let's say, 1 second, and they decided to do a re-election to elect a new leader. But now, immediately that re-election happens, the GC pause was over from here, and they now got a request from a leader. But this leader was the previous leader. So we need some mechanism to detect if the requests which are coming to me are from legitimate leader or from a node which was partitioned for some time, or there was a GC pause, like a soft failure on that node. So to detect this, again a very simple mechanism that's used, that there is a number maintained. After every leader election, that number is incremented. And this number is then stored with every write-ahead log entry, every message that is communicated with to all other servers. Like any message that leader sends, this number is part of that message as well. So if you see what happens here is, let's say, for the first time that number was 1. And the messages that the leader is sending is with that number 1, the generation 1 message. When there is a pause or a network partition, the re-election happens, and that increments that number, that increments that generation number or a term number in case of Raft to 2. And after that point, any request that server gets, it will reject it. It will say that I reject this request because I am at generation 2 or I am at term 2. And that's how the previous leader will also know that I was disconnected from the rest of the cluster and the rest of the cluster has moved ahead. Again, this is, as I said, because this is a pattern, you will see that even in things like Cassandra. Like when there are things like hinted and handoffs implemented, when a server failure is detected, you also need to detect if server is back up. Like it was down, but now it's back up. And the same concept of generation is implemented in Cassandra as well. The same number which is incremented, and if the request that I get, or any node gets, it compares that the number that I am getting, the generation number that I am getting is now one more or higher than the number that I had. That means that server has restarted. So putting it all together, any consensus implementation or any distributed system implementation you look at, you will see these patterns. I mean, it resolves around essentially replicated write-ahead log. And to implement replicated write-ahead log, you need to have concept of quorums, leader followers, heartbeat, a synchronous channel, singular update queue, a concept of a generation, and also high watermark to be able to apply this. Cool. So that's, yeah, so that's, I think, the end. You guys have any questions? Yeah.
Hey, hi.
Yeah.
So when you are writing to the write-ahead log,
Yeah.
isn't that operation itself vulnerable to crash? As in,
Yes.
What will be the?
So essentially, if you cannot write to write-ahead log, that operation crashes, right?
Correct.
Then your client will get a failure. If you cannot write to write-ahead log, your client will get a failure.
So like the atomicity is preserved in a way.
Yes. Yes.
I have two questions.
Yeah.
The first one is there a concept of cluster change notification in Raft? So instead of heartbeat, I mean, or even if...
There is a configuration change mechanism, yes.
Okay.
Yes. So you can, so yeah, I mean, essentially I didn't talk about those things, but nodes can dynamically be added to the existing cluster, and then you get a configuration change notification. Yeah,
Okay.
it is there.
The second
I mean, you need that because, I mean, what I talked about mostly, assuming that you have fixed set of servers, but typically you need dynamic membership.
Second question is regarding the client. So client always connects to the leader.
Yes.
And when there is a failure and leader changes, how does client deal with it?
No, client will typically retry.
Okay, so it
Yeah,
will time
you'll
out,
get
the
a
connection
get a
will
exception.
break,
Yeah,
and then it
yeah.
will again scan the entire cluster to find out the leader.
No, I mean generally, I mean different implementations work differently. Like most consensus implementations, you can connect to any server and it will forward it to the leader. But if the metadata is available to you, like in case of Kafka kind of implementations, then the client can get the latest metadata and detect what the new leader is and forward it to forward the request to the leader.
Okay, I understand that. Suppose you
Yeah.
are connected to a particular address.
Yes.
So whether it's a follower or leader,
Yeah.
or whether follower is forwarding the request is a different question.
Yes.
But whatever connection is there, suppose it breaks. I mean,
Yeah, you will need to try that again. Yeah.
then the client has to
Client
know
has
the
to retry.
pool of IP addresses that it can connect to, right?
Yes.
Okay.
Yes.
All right. Thank you.
Hey, so you mentioned that if the request is routed to any of the followers, it will route it to the leader. So is there a way we can register the follower or the leader with the service discovery, maybe, so the client, when it calls it, it does not have to do all the routing?
Yes,
and
yes, possible. Yeah, that's what I said. So if the metadata is available to you, either through service discovery or explicit metadata mechanism, metadata handling mechanism, then a client can know about leader upfront and then go to that leader. Yes.
Cool, thanks.
Hi. So how does the brain split scenarios gets handled in this condition? Take an example. You have say a cluster,
Yeah.
and half of the nodes are able to connect to the leader, but they and half of the nodes are not able to connect to the leader, and it's just a very minute change. For the fraction of seconds, say, and you have a protocol designed like after 1 second, if you are not receiving the heartbeat from the leader, you
Yes.
decide that leader is dead. But
Yes.
actually, that is not the case.
Yes.
So in this scenario, two clusters has formed.
Yeah, no. So two clusters will never form because if every operation that you do, including leader election, it requires quorum, like the majority that should be reachable from yourself. Then you will never have. So you will still have network partitions, but you won't function. So you.
Take an example of bigger clusters. Say.
So yeah,
And
let's say
so-
5 node, 7 node, any number of nodes. Your functioning can stop. Now, one of the disruptions that can happen because of these kind of network partitions is that the followers which are partitioned away, they can trigger new leader election because they detect that there is no heartbeat coming to me from leader, and it can cause disruptions because every leader election increments that term, and the other followers need to now say that, okay, this is the new leader. So there are special handlings that need to happen in the leader election algorithm to prevent this kind of thing. So I think Raft thesis specifically talks about these kind of disruptions because of network failures or network partitions, temporary network partitions. But cluster as a whole will be always in a consistent state. So worst case, what will happen is it won't function, but it won't lose consistency.
Thanks.
Hi, Unmesh. So wondering why you did not share the code snippets in Akka or something, because that seems to be a perfect fit for the single update thing that you were trying to talk
Sorry.
about, right? The Akka actor.
Akka actor, yes.
I mean, we could have represented everything as a process right there, and
I mean, you can use Akka actors, yes. And there is a Raft implementation by the Akka guy as well, Conrad.
yes.
That is available. But for implementing something like Zookeeper or etcd, I mean, even if for modeling and coding, it fits really well with actors. Typically, the choice is not to use any other heavy framework because there are a lot of system level things that you need to tune. So typically, they don't use these kind of heavy frameworks. But some of the similar patterns, if you see, are implemented in Flink, like Apache Flink, and that heavily uses Akka actors. So yes, I mean, like for modeling, it is the perfect thing. But for systems level frameworks, it is not used generally.
I was just looking at a bunch of Scala code up there.
Yeah.
So I was like,
It is Scala.
If you're already using Scala, instead of throwing a new runtime exception, we could have actually written that in Actor and probably get it.
Yeah, but Actor, the thing is that Akka Actors is a pretty heavy library. And generally, as I said, for writing these kind of system level frameworks, you won't depend on, generally don't depend on another heavy library.
Thanks.
Hi, this is a follow-up question to the question before the last one. So in a situation where you've got some I/O happening in a cluster, okay, maybe I/O to a shared disk or something like that, and this is a tight cluster which is using some sort of a consensus algorithm, and then there is a failure where maybe there's a split brain, and because of that I/O is happening from two nodes in two different parts of the cluster, and all of the data has not been flushed. Is it possible for the leader election algorithm to actually take care of such scenarios?
No, it won't happen, right? I mean, so the thing is that if you have a network partition, you don't reach quorum of your servers, those requests will fail. So you will never have a situation where writes are happening concurrently on two parts of your cluster, and you somehow need to reconcile. That won't happen in consensus implementations. That will happen in databases like Cassandra, maybe, because you are writing concurrently to multiple nodes, and then reconciliation happens at the read time. But consensus won't function. Your write requests will fail if they can't reach a quorum.
Exactly. So the assumption here is that there is a hard quorum. If you have
yes,
n clusters, it's always going to be n by 2 plus 1 or whatever.
Yes.
Without that, but in many practical cases that doesn't seem to be the case, right? I mean, if you gave the example of Cassandra, and in such cases,
yeah, but the implementation is different there, right?
What I mean is that you perhaps need some mechanism beyond just the consensus algorithm in such cases to take care of preventing data corruption due to concurrent IOs. Because you're not preventing concurrent IOs if you have a flexible quorum, where you have a smaller, you've set the read quorum, the write quorum to be less. Maybe you're just
no, but the thing is that in consensus, that choice is not given to you. The choice is fixed in the algorithm depending on number of servers which are part of your cluster. So in case of Cassandra, yes, because it's eventually consistent by design, you can choose your write quorum to be smaller. I mean, like, same in case of Kafka, right? I mean, those are not same as consensus algorithms.
Yeah, they are not linearized.
Yes, they are not that. And when the implementation is like that, then you need to tolerate some inconsistency or take care of that inconsistency while you are reading, and then resolve that somehow.
Read repairs.
Yes. So you need to have some repairing mechanism that's running parallelly. Either a repairer service like what happens in Apache Bookkeeper, or you need like read repair or things like that. Cool. Thank you. So the code is available on GitHub. I will share the link. I think I didn't show it on the screen. So go ahead and play with it. I think it will be helpful. Thank you.